What I will do this time is I create a second capsule object and start working on the collision between two capsules. At the end of the video, I will get the linear collision done. In this episode, I'm going to implement the collision detection, the penetration resolution, and the linear collision response between two capsules. So first of all, I create one more capsule called Caps2. And I push this one a little further to the right. And let's check. I need to make sure that I only control one of them, for which I need a player property that is false in default, and I set it to true for the first capsule, and I only call the key control method for the capsule that has the player property set to true. Yep, that's better. And instead of painting these capsules to light green in the draw method, I'm going to display their central line segment by drawing a line from its start point to its end point. And let's check it. Yeah, this is what I mean. For the ball-to-wall collision, I wrote a function that finds the closest point on a line segment to a given coordinate. Here is the function, and that coordinate was the central point of the ball. And I used that closest point to determine if its distance from the ball's center point is shorter than the ball's radius, and if it is, then there is a collision between the ball and the wall. To determine if two capsules are overlapping, I will use a function that is based on finding the closest point on the line segment. The reason it's based on the previous function is that I will calculate the distance of line segment's endpoints from the other line segment, and that will mean 4 cases: this one, this one, this one, and this one. And the smallest result of these 4 cases will be the shortest distance between the two line segments. So in this case, that would be something like this, more or less. This only works if the two line segments are not intersecting, but ideally that will not happen because the penetration resolution is supposed to prevent that. To be able to reuse this function, I will need to make some changes. First, I need to modify the first argument, which here is a ball, but that wouldn't work for the case of the capsule. Instead of that, it will be a single point. And whenever I call the function, I will give the ball's center point as the first argument if I want to use a ball for the first argument. And the orientation unit vector for the wall is the wall unit method. I couldn't use this function now for walls and capsules both, because the capsule doesn't have a wall unit method and the wall doesn't have a direction property. So I will give a direction property to the wall object, to the wall class, instead of the wall unit method, for which I go to the wall class and I cut this expression here and delete the wall unit method. Then in the constructor, I'm creating a dir property, which stands for direction, and this will be the orientation unit vector for the wall from now on. And I also want to give a new name for this function, closest point on line segment, because it's not necessarily a wall anymore. And whenever this function gets called, I need to use this new name. And also I need to give the ball's position as the first argument, because the first argument from now on is a single point and not a ball. And that should be it. Now I should be able to use this function For the case of the two capsules, I create a new function called closest point between line segments, and it will take two capsules as arguments. What this function does is it calls the point to line segment function 4 times for both line segments to endpoints. Then it will pick the minimum of those 4 distance values, and it will return with an array that consists of the 2 points that are the endpoints of that line segment with the shortest distance. So what I do in this function is I create a shortest distance variable, and the value of that variable will be the distance between the first line segment start point and the second line segment. Then I go through 3 other cases. I compare the distance between the first line segment's endpoint and the second line segment. Then I check the second line segment starting point with the first line segment and the second line segment's endpoint with the first line segment. And whenever the distance of the 2 points that I'm checking is shorter than the value of the shortest dist variable, then this variable's value will be replaced to this new distance. And together with that, the 2 points that are in the closest points array will also be replaced to the currently checked 2 points. And once I go through all these 4 cases, I can return with the array that consists of those 2 points that are the closest ones to each other. And I want to visualize that shortest line segment to make it easier to understand. So I write here some extra lines in this function that I will delete later. I will draw a line that connects the closest points, and I also put a circle around those points with the color of red, and those circles will have the same radius as the capsule around them. I rewrite this here to line, and now what I need to do is calling this function down in the main loop using these 2 capsules arguments. Let's see if it's working, and it looks like it does. I can see the shortest line segment between the 2 capsules, which is good. Now that I have this function ready to use, I can move on to implement the collision handling. I already know that I will need 3 functions: the collision detection, the penetration resolution, and the collision response. So I create these 3 and just leave them empty for now. And in the main loop, I call them when I iterate through the capsule array. And I need the index argument in the for each loop. Then I can go back to the collision detection, and it will actually be very similar to the ball-to-ball collision, because I can handle these 2 points in the capsules as ball centers and the capsule radius as ball radius. And then it's reduced to a ball-to-ball case when the distance between these 2 points is smaller than the sum of the radiuses, then the balls overlap. And if they do, then so do the capsules. So I can copy the code from the ball-to-ball collision to here, and I replace the B's to C's, and the magnitude I'm comparing the sum of the radiuses to is the distance between the 2 result points of this function. And to test if it's working, I'm displaying something on the canvas whenever this function returns true. So I should see this collide word on the canvas if they overlap, and that's what happens. And if they don't overlap, then the word is not there. That's good. I can move on now to the penetration resolution function, which is here. The penetration resolution can also be reduced to a ball-to-ball case. So I can again just copy the code from the ball-to-ball case and paste it here and make a few little changes. So what happens here that I calculate the penetration depth by subtracting the 2 points distance from the sum of the radiuses. Then I multiply the unit vector, which points from the first point to the second point, that's the collision normal, by the penetration depth. And I move the two capsules away from each other along the collision normal, proportional to their inverse masses. Since this function uses the mass, I need to create the mass property in the capsule class that comes with an inverse mass property. And the mass will get the value from the argument list. And when I instantiate these two capsules down on the bottom, I have to set those values. I will set them to 2 and to 3. And I check if it's working. And now it's not only detecting the collision, but also is able to push the other capsule away. That's good. Now I can do the collision resolution, which will be also similar to the ball-to-ball case. In this episode, I'm only handling the linear velocities change, and the rotation comes later. So again, I can just copy from the ball and modify a little bit, like replacing the B's to C's and choosing the normal vector in a bit different way. So I take the relative velocities projection along the collision normal, which will be the separating velocity, and if the collision is elastic, then the separating velocity will be multiplied by -1 when the collision is detected. And the difference between the separating velocity before and after the collision will be distributed to the capsule's velocity, which will be the impulse vector, and that's proportional to their inverse masses. And since I use elasticity here, I need to add it as a property to the capsule class, and I just set the default value to 1 because I want them to have an elastic collision. It looks better if they bounce apart. And let's check it. It's very good. But the point of creating a capsule class was to implement the collision that includes the change of the angular velocity, which will probably take a long time relatively, so I will only do it in the next episode.